This is my paper review entitled Efficient Hydrogen Production on MONI4 Electrocatalyst with Fast Water Dissociation Kinetics. In introduction, in many of the approaches to hydrogen production, the electrocatalytic hydrogen evolution reaction, or HER, from water splitting is the most economical and effective route for the future hydrogen economy. To accelerate the sluggish HER kinetics, particularly in alkaline electrolyte, highly active and durable electrocatalysts are essential to lower the kinetic HER upper potential. Various platinum-free electrocatalysts have been explored for hydrogen evolution reaction in acidic solutions. However, in economical water alkaline electrolyzer, sluggish water dissociation kinetic, or former step, in platinum-free electrocatalysts result in poor hydrogen production activities. And here in this paper, the authors report MONI4 electrocatalyst support by MO dioxide cuboids on nickel foam, which is constructed by controlling the outward diffusion of the nickel atoms on annealing precursor nickel moly oxide cuboids on nickel foam. In experimental sections, MONI4 nanoparticles with a size 20 to 100 nanometer are constructed in situ on the moly dioxide cuboids by controlling the outward diffusion of nickel atoms when the previously synthesized by nickel moly oxide cuboids are heated in the under argon and hydrogen atmosphere at 500 degrees Celsius for 6 hours. Result and discussion: structural characterization of MONI4 electrocatalyst, and I took this figure from supplementary document. And in order to remove the crystalline water from nickel moly oxide, the initial of this name was heated at increased the temperature from 200 to 400 in argon atmosphere. And we can see from the XRD, the XRD diffraction peaks of the obtained sample at 400 degrees Celsius accord perfectly with the standard peak of nickel moly oxide, or NIMO04 to the PDF 330948. As shown in figure 2A, B, and C, numerous nanoparticles with size in the range of 20 to 100 nanometers are uniformly anchored on the cuboids, which are vertically aligned on the nickel foam. Clearly, the high-resolution TEM image of the sample shows lattice fringe with lattice distance of the 0.35 and 0.28 nanometers, which correspond to the 110 facet of moly dioxide and the 200 facet of MONI4 respectively. The selected area electron diffraction pattern show the diffraction pattern of the 200 facet of MONI4 and the 110 facet moly dioxide. We are insert in this figure. Based on figure 2C, this is the sample where calcinized at 500 degrees Celsius for 2 hours. The outer part of the cuboids undergoes the phase change and forms the nickel moly oxide phase, where the nickel becomes transferred into dots while moly dioxide covers the cuboids. It can be confirmed via X-ray elemental mapping as shown in figure 2G. We can see the gray mapping color is in situ MONI4 and moly dioxide cuboids growth, and the green mapping color is molybdenum, the red mapping color is oxygen, and the bubble mapping color is nickel. The XPS analysis was carried out to probe the chemical consumption and surface valence states of MONI4 nanoparticles and the supporting moly dioxide cuboids. XPS peak of metallic molybdenum and nickel are observed at 229.3 and 852.5 electron volt respectively, further confirming the existence of molybdenum metal and nickel metal in surface of the MONI4 moly dioxide in nickel form. As displayed in figure 3a, the nickel nanosheet on nickel foam has a very high over potential of around 253 millivolts at 10 milliampere per centimeter squares, where the molybdenum dioxide cuboids on the nickel foam has an over potential around 48 at 10 milliampere per centimeter squares, where in addition, for the supported MONI4 electrocatalyst, the over potential at current density 10 and 200 milliampere per centimeter squares was as low around 15 millivolts and 44 millivolts respectively, which were significantly lower than the values of the nickel nanosheets, molybdenum dioxide cuboids, nickel moly oxide cuboids, MONI3, MO2 cuboids. Figure 3b displays the table plot of the corresponding polarization curves, which provide profound insight into the fundamental HCR kinetic mechanism occurring on the surface of the electrocatalyst. The table slope of the MONI4 electrocatalyst was as low as 30 millivolts per decade, which is far lower than the values of 129 millivolts per decade for the nickel nanosheets and 75 millivolts per decade for the MO dioxide cuboids, and highly comparable to the PT-based catalyst. This result indicate that the electrocatalytic HCR kinetic on the MONI4 electrocatalyst were determined by the table step rather than a coupled former table or former perovskite process. In other words, the prior former step has been significantly accelerated. In figure 3c, this is the comparison MONI4 with others sample with selected state-of-the-art HCR electrocatalyst. Long-term electrocatalytic stability is another important criterion for HCR electrocatalyst. In addition, a long-term electrocatalytic HCR process was successfully carried out at the current density of 10, 100, and 200 milliampere per centimeter square. The inset in figure 3D demonstrate the MONI4 electrocatalyst retain a steady HCR activity, and only increase of around 3 millivolts in potential was observed at a current density of 10 milliamp per centimeter square after a period of 10 hours of hydrogen production. The overpotential required for large current density of 100 and 200 milliamp per centimeter squares was augmented by only 2 and 5 millivolts respectively. In figure 4a, this is the illustration of the molecular bond and calculated free energy, where the blue balls is nickel, aqua balls is molybdenum, red balls is oxygen. Molybdenum dioxide from this part. Molybdenum dioxide has a large energy barrier for the former steps is equal to 1.0 0.01 electron volt, and a strong hydrogen absorption free energy is equal to 1.21 electron volt, indicating a very sluggish formal step mechanism. Thus, molybdenum dioxide is not very highly active center for the HER, which agrees well with the experimental result. Figure 4b is calculated absorption free energy diagram for the former step. As shown in this diagram, the Gibbs free energy towards water on MONI4 is significantly decreased to 0.39 electron volt, which is even lower than the value of 0.44 electron volt on PT. From figure 4c, in addition, MONI4 has a lower hydrogen free energy of 0.74 electron volt than the value of 1.21 electron volt for molybdenum dioxide, which correspond to a superior hydrogen absorption capability. Thereby, the HCl reaction on MONI4 is associated with a process defined by a fast stable step rather than a sluggish formal step. In summary, as favored by a largely reduced energy barrier of the former step, the achieved MONI4 electrocatalysts exhibit a high HER activity under alkaline condition, which is highly comparable to that for PT and outperforms any reported result for the VT-free electrocatalyst. Thank you.